In this video, we'll cover another consensus algorithm, what's known as the Delegated Byzantine fault tolerance. We'll discuss how it works, potential challenges with it, and who's using it. The Delegated Byzantine fault tolerance, or DBFT, is a consensus algorithm based on assigning roles to different nodes to coordinate consensus. Now, how does the Byzantine fault tolerance work? DBFT does not have minors. Instead, it has nodes that are split into ordinary nodes and consensus nodes. The majority of nodes in the network are just ordinary citizen nodes that can transfer or exchange assets, but they don't participate in validating blocks. Consensus nodes have the power to verify each block written to the blockchain. Consensus nodes act as a representative for the other nodes in the network, similar to how an elected government official would represent the majority of its constituents. For an ordinary node to become a consensus node, it usually needs to meet certain criteria, which differ from platform to platform. So these may involve owning some special equipment, having dedicated internet connection, or having certain stake in the network. Consensus nodes keep track of proposed blocks that could be added to the blockchain. When it's time to decide which block should be added next, a consensus node is randomly selected from the pool of all consensus nodes. In the Neo blockchain, this chosen node is called a speaker, and all the other consensus nodes are called delegates. The speaker creates a new block and proposes it to the delegates. 2/3 of all the delegates need to approve this block before it's passed. If it doesn't pass, the chosen speaker returns to being a normal delegate and another speaker is chosen. This new speaker proposes their truth, which block should be added, and this block is put up to vote. If it passes, the new block is added to the blockchain. DBFT is said to be much faster than proof of work, and it requires less resources because there are no complicated cryptographic puzzles to solve. Additionally, it's resistant to forking because at any given moment, there is only one version of truth. With that said, DBFT is not immune to problems. Let's take a look at two potential scenarios. In the first, let's assume there's a dishonest speaker. There's always a chance that the speaker, who was randomly selected from the delegates, could be dishonest or malfunction. And if this occurs, the network needs to rely on honest delegates to vote the proposed block down so it doesn't reach the 2/3 approval rate. Since users of the protocol vote on delegates, and the speaker is randomly selected from the group of delegates, it's up to the users to find out which delegates are trustworthy and vote them into power. Let's take a look at our second scenario. It is up to users who vote on delegates to do their due diligence to only vote honest delegates into power, so that dishonest delegates are in the minority. If a minority of delegates are dishonest, the honest majority can vote the block down, and the block won't make it into the blockchain. To help with this, some blockchain platforms release data about the honesty and functioning of each delegate for voters to review. So who uses the Delegated Byzantine fault tolerance? Well, Neo has been one of the biggest advocates for this protocol. It is a blockchain platform and cryptocurrency designed to build a scalable network of decentralized applications. While proof of work and proof of stake are definitely the more popular choices, newer mechanisms continually pop up and prove themselves. Remember that a consensus algorithm gets its reputation from being safe for a long period of time. For example, Bitcoin has stayed a safe network since its inception in 2009. With that said, there's no perfect consensus mechanism, and chances are there never will be. But it's interesting to see newer blockchains coming up with their own mechanisms, and it's equally interesting to understand their pros and cons.